I will I will now talk about a different type of data structure for representing dynamic sets. Okay, so as a reminder, we are talking about representations of dynamic sets. These are sets that can expand and shrink, as in we can add elements to them, we can delete elements from them. Remember that three operations that are very important to us are searching in a dynamic set. We have insertion, we want to add an element to a dynamic set, and deletion. We want to delete an element from dynamic set. So in general, such a structure, dynamic sets that have these kind of operations defined on them, that's what's referred to as dictionary. Okay, so we have a dictionary and we want to represent it so that we have these operations implemented in efficient way. We have seen binary search trees and balanced binary search trees as one way of implementing dictionaries for dynamic sets. And usually they give us we show there the log of n running time for many of the operations, because the balancing of these trees resulted in the height being on the order of log of n. Now we will talk about hashing or hash tables, which is a different data structures. Okay, a hash table is also a data structure, but it's very different from binary search trees. They are very efficient, and the focus when we talk about hash tables is really on the average case analysis. Okay, so why do I say this? And it's very important to say it up front, because hash tables do not do magic. In the worst case, they can still behave like a linked list, that if you want to search for an element, you have to scan the entire list. Okay, that's in the worst case. But hash tables, on average, they do very well in that they allow these operations to be done in O of 1, which is of course huge, because this is we are talking about constant time to search, to insert, to delete in a hash table. Now, hash tables are really extensions of arrays, and arrays are all over the place. We have seen them, you use them in implementations, in programs, and so on. If you think about an array, that's what's known as direct addressing. Okay, so if you think about an array, and where the array is, let's say, a from 0 to n. So this is an array for n, this is my n minus 1 here, for n elements. And I have a set of elements. Let's suppose I have a set of elements. And let's say that the elements are 1, 3, 2, 2, and 9. And suppose that the n is 10. So we have an array that from 0 to 9. And now when I want to basically, I represent these elements, I store them in an array. So element 1 goes to entry 1 here, and element 3 goes to 3, and 2 goes to 2, and 9 goes to 9. So now if I want to find if 3 is in the data set, and suppose this is called T here, the table T, and if I want to find is 3 in this table, I can just go to T of 3 and say does it have an element or is it nil? Okay, if I want to insert an element, so suppose I want to insert 5 into the set, I add 5 to the set, then I can go to T of 5 and say, is there something there? If it is, I need to add it. If there is nothing, I need to chain it to it. I add it as another element. Otherwise, we just insert it as the first element. If I want to delete T of 9 or key 9, I go to T of 9, and if the element is there, I delete it. All of these operations, searching for an element, insertion and deletion in an array, which is again direct addressing. This is known as direct addressing. This is all done in O of 1. Okay, now I want to say one word here about the keys and what is really being stored here. So if I look at key I here, what's stored there is not just the value I. Again, remember that these data structures, whether the binary search trees or even the hash tables, these are data structures that are underlying the implementations of databases. They are used in compilers. They are used all over the place. So when we talk about a database, what we are storing in a database are not just a bunch of numbers. We are storing these records. So again, for a student, for example, at Rice, I would have a record for the student where the key could be the student ID. But in addition to that key, so we would have the student ID here, or which is the key in our case. But then we have other types of data in the record: the first name, the last name, the middle name, the date of birth, all of that kind of information. This is what's known as satellite data. Okay, satellite data. So the record has so much data in it, but we are usually looking up that record or inserting it or deleting it based on a key that we decide what it is. Again, it could be based on the student ID, for example. So when I'm talking all the time about keys, please keep in mind that we are focusing on keys because that's the value based on which we are doing these three important operations. But this key, attached to this key, is so much information or so much data that we don't focus on usually, but that's part of what's stored there. Okay, so in an array we have this direct addressing, in which case we can do insertion, we can do deletion, we can do search in O of 1. So everything is great. Okay, now the problem with this is that usually, if I look at this set here that I drew of the elements, this is, we have a universal set of keys. So we have universal set of keys. This universal set can be huge, it can be even infinite. I mean, the keys can be integers, okay, or natural numbers, let's say, non-negative numbers. So universal set of keys can be huge. The actual keys that we might encounter, the actual keys that we might be looking for, the actual keys that we might be insertion, deletion, that set is, let's call it big K here. This is the actual set of keys, actual set of keys that we can encounter in the dynamic set, okay? And K is, of course, a subset of U. Okay, so U, let's say U is all the natural numbers. K, we might be dealing with numbers that are at most 1,000. Okay, so K can be between 0 and 1,000. And with an array, we have a great representation of this, because if the cardinality of U, let's say, is in, the cardinality of big K is small k, then we can easily do this. So this is the set big K and this is the set U. We have here an array that goes all the way from 0 to 1 to n minus 1, and then we can map these elements here. Okay, and this is why we usually like arrays, as in they are easy to implement and the operations, the insertion, deletion, and search on them is O of 1. But of course, there are two big issues with arrays. The first one is, if U is too large, then this implementation is infeasible. Arrays are infeasible. What do I mean by infeasible? If U is 500 trillion, okay, so I am saying that the keys can be in this huge set that has 500 trillion elements. Do you really want to declare an array in your program that has 500 trillion elements? I mean, that's the amount of memory there is just enormous, okay? So, and again, keep in mind that U could be infinite. So, but infinite as in, we can put a very large number as the cardinality of U, but this is infeasible. I mean, the amount of memory that we end up allocating is huge. The second one, it has to do also with the size of U, but also K can be too small. If the size of k is much smaller than the size of u, then we have a waste of space, right? Because imagine that you allocate an array of 5 million elements, and k, the size of k, is 5. Okay, so there are 5 keys that you're going to be using. So in this case, you have wasted so much space by allocating all that memory in the array for set u, even though you're going to be dealing with a very small subset of that set u. Okay, so now we have U, and big K. Again, U is the universal set from which the keys can be used. Big K is the actual set of keys that we can encounter. So for example, U can have the value 19, and 19 we might not encounter it at all, so it will not be in big K. Okay, so what is the objective? What is the objective with when we talk about hash tables and hash functions? We want to reduce the amount of space. We want to reduce the amount of space to some theta of the size of k. Okay, so we want the space that we use to be on the order of the size of k. Okay? And this is a huge gain, because if k is much smaller than big U, then we are not wasting any space here. We are just allocating space that is needed. Now, we want also the average case running time of the search operation and insertion and deletion to be O of 1. Okay? So this is really our objective here, that we don't want to use all that space in an array that we are going to be wasting, other than, again, it could be infeasible even to allocate that amount of space. We would like to have space that's on the order of the actual number of keys that we will use, okay? Keep in mind, this is theta of k. So, if k has 1,000 elements, the amount of space we could be using is maybe 2,000, 3,000. There's a constant there, okay? So, this is what brings us to hash tables and hash functions. Okay, so a hash table that it's basically a table, let's say from 0 to m minus 1. Here, let me, m is the size of the table. Okay, m is the size of the table, and we want to map the elements in our set to this hash table, or what we say is that we want to hash the elements to this hash table using a hash function. So what is a hash function? It's a function that maps every possible key in the universal set of keys to one of the indices of that table. Okay? Remember that direct addressing, as in arrays, you can think about it as one simple hash function, which is the identity function, right? We are mapping key k to entry k in the array, okay? We are mapping key 5 to entry 5 in the array, and so on. So hash function is, we're not going to be using the identity function, but it's going to, you want to store key 5, we are going to apply function h to 5, so h of 5 might be 20, then we are going to store 5 in entry 20 in the table, okay? And a key issue here is that m is much smaller than the size of u, okay? This is the assumption, that u is very large and m is much, much smaller to it. And when we do this, we are saying that key k, in terms of, just jargon here, key k is hashed to, or hashes to h of k, okay? So if you want to look up the key k, basically you need to look at the entry t of h of k. So here, this is the entry where you would find key k if it is stored in the array. If you want to insert key k, you insert it in t of h of k. If you want to delete key k, you delete it from t of h of k. Again, remember that for an array, h of k is k. Okay, this is for an array. So basically, it's the identity function. We don't need to evaluate the function itself. You want to insert key 5, go to entry 5. You want to delete key 5, you go delete from entry 5. With the hashing function, you don't go to 5, you go to h of 5, okay? And the way it works is, again, that we still have this universal set U, and we have this smaller set big K, and we define this table here. The table, again, is of size m, so it goes from 0 to m minus 1, and then we have all these keys here that get mapped to some elements. Okay, and I drew here something very, specifically I drew it like this, that notice that if we have key K1, K2, K3, K4, what I am trying to illustrate here is that h of K2 equals h of K3 equals h of K4, okay? And this could happen depending on the function you define. Maybe the worst possible function for this is h of k equals a constant, okay? So imagine I map all the keys to entry 5 in the array. That's a hashing function. There's nothing wrong with it. It is a function. It is from u to 0 to the set 0 to m minus 1, but it's such a terrible function, right? So I can define h of k to be 5 for every k in u, okay? This is a hashing function. What does this do? It hashes every element in the universe of keys to the same entry there. So if you have, the set K has million keys, you are mapping million elements to the same entry in the array. Now, this issue where you can have multiple keys hashing to the same place is known as collision, okay? We have a collision because we are trying to insert a key into that table, and we find that there was already a key mapped to that table. So these two elements collided in the table. So we have a collision. Now, this is really what all the research or all the work on hashing is about. Now, since the size of U is much larger than M, by the pigeonhole principle, collision is inevitable. Okay, we cannot avoid it. Collision is inevitable, okay? It's unavoidable to have collision. You're not going to be able to, in practical cases, to find a function that will never ever map more than one element to the same entry. So what is it that we want to do then with hashing? What is all the work about hashing? Why do you have a textbook that has 20, 30 pages on hashing, and then you can go and Google and find tons of more papers about other hash functions and so on? What is that all about? Of course, there are two desired properties. The first one is that we want to minimize collision. Okay, we want to minimize collisions. And it's important to emphasize minimize, not to avoid. We cannot avoid collisions. This is impossible in practice to avoid collisions, that we have some fancy function that will never map two keys to the same entry. So we would like to minimize that, okay? And usually when we say we want to minimize that, we would like for the function to be in some sense random so that it uniformly maps the keys to the table. So imagine that M is 5, let's say, and the set K has 20. One way is that to map one element to entry 0, one element to entry 1, one element to entry 2, one element to entry 3, one element to entry 4, and then the remaining 15 elements, all of them map to 5. That's not great. We prefer that every entry gets on the order of about 20 divided by 5, which is 4. We would like for every entry to get about 4 keys, roughly speaking. So this will be a great hashing function, because this is a function that will minimize collisions. Yes, we will have collision in every entry, but we are not going to have that terrible situation where we have one entry that has a very long list of keys, okay? The second one is that we need to think of ways that once we have collisions, how do we resolve them, okay? Resolve collisions, okay? What do I mean by resolving collisions? So again, let's go back to this table T here and imagine that I have K1, and K2 and K3 and K4, all these keys map here. So what do we do in this case? So one way to do this is, for example, is what we call resolving collision by chaining. So we have here K1 with its satellite data, and then we have a linked list basically, and K2 with its satellite data, and K3 with its satellite data, and K4 with its satellite data. So basically we have created a chain of the keys that map to this entry. Okay, so this is one way of resolving this collision, as in, if you hash an element to an entry and there's already an element there or more than one, you just attach that or chain that to the existing list there. Okay, and this is going back to the issue of minimizing and having a good function. Again, I was trying to illustrate. So imagine that u, let's actually take it as, simple case. U is from 0 to 19, and m is, let's say, 4. Okay, so from 0, 1, 2, 3, 4. So we have a table of 5 entries. So so this is 0, 1, 2, 3, 4. So here's one hashing function that will say h of 0 equals 0, h of 1 equals 1, h of 2 equals 2, h of 3 equals 3, and h of I equals 4 for every I between 4 and 19. Okay, so this is a hashing function. There is nothing wrong with it as a function. It is mapping all the elements of U to the set 0 to 4. But this function is going to have one element here in 0, one element here, one element, and one element here. And then it's going to have this linked list of 15 elements in it, or 16 elements in this case, right? So this is going to be a very long list. And we have collision here, but this is a terrible design of this function, because if you are looking up for, if you want to insert in 4, if you want to delete from 4, or especially if you want to search for an element that mapped to 4, you might have to go scan this entire list, which is a very long list. What I was saying with better design of a function that will minimize collision, that imagine that instead of that, we have a function that allows us to do this 1, 2, 3, 4, and here we have a list with each one of them is a list of 4 elements, something like this. Okay, so imagine that we had such a function that will allow us to map about 4 elements to each entry. Notice that we have mapped all 20 of them to that. This is much better, because when you are searching, every search here, you will go in O of 1 you compute h of k in O of 1, you hit the right entry there, and you scan the list. Well, the list has 4 elements. Now, in the previous one here on the top, if I map h of k is 4, then I have to scan a very long list. Okay, so these are the two points that we want to focus on when we talk about hash tables and hashing functions. The first one is we don't want this situation on the top there. Okay, we don't want this case where so many keys map to one entry that created a very long list. We want to minimize this. The second thing is that we need to think about, once we hash an element to an entry in the table, and that entry already has a key, how do we resolve this collision? Okay, this is really all research in hashing is all about. And there are so many techniques for designing these functions, and this is still an active research area, actually designing hash functions. Today's functions are even more sophisticated than what we are going to cover in this part of the course here. But so much research is done into how do we design a hashing function this age such that we optimize the running time by avoiding these very long chains due to collision.